A block cipher always encrypts a block of 128 bits into the same encrypted block. So if you see an encrypted block repeatedly, you may start guessing that it might mean something special. So that leaks information to an attacker who might not know exactly what's the block, but might start guessing. And the goal of an attacker is not to be certain about the true thing, but it's enough. If you have a very small probability of succeeding, you will have you will do millions of attacks, and if one of them succeeds, then you succeed. If the attack consists in taking the credentials, guessing your password, or gaining access to your bank account, it's sufficient to succeed once. Whereas for us, for the defender, it's sufficient to fail once to be lost. Right? So there is this asymmetry. We've seen that with AES we need a nonce to avoid that problem, and the idea is you change every block by adding a number that changes for every repeated operation. So if the same block is seen many times in a message, for example, protocol headers are most of the time always the same, or if you send a PMU measurement, there will be text about this is PMU measurement for PMU so-and-so. There will be also lots of zeros that will always be encrypted in the same way, except if we modify them by adding a nonce. Here, it's very similar, but it's not a nonce. So it's the same building block. The building block is AES block encryption. But here the goal is different. We still need a key. So the MAC uses a secret key. Then we take, as first thing we encrypt, this, that means the length of the message. So the first block we encrypt is the length of the message that is encrypted with a secret key. And then the result of this encryption is used with the first block of the message to which we want to add a tag, XORed. So we do the bit by bit XOR thing. That's a way of merging a message with some previous text. That's what is used with the nonce. Here it's the same thing is used, but this is not a nonce. This is a part of the message information. That creates a second block, and we chain this. So it's very similar to CBC MAC, where in CBC MAC we use here an initial counter that is used with the message. But here it's different. The counter, if you want, is the message length. And at the end, we obtain only one thing, which is the tag. When we do encryption, at every stage we obtain a block that we will use. Here it's only the last stage that is interesting for us. The tag is therefore much shorter than the message itself. But if it's long enough, like 128-bit, it's very hard to attack this one, other than by brute force. And brute force will be very difficult because it's long enough. We believe that AES is secure, which means it's impossible to guess what from a ciphertext or from a tag here, what was the M3, for example, for somebody who doesn't know the key. So we believe it's impossible, other than by trying all possible cases, it's impossible to get up here and obtain M3. Therefore, it's also impossible, it's even worse, more difficult, to get back to the entire chain. So it's impossible to get back, but also to forge a message here. Now, the way I presented the MAC, everything is sent in the clear text, right? It's not designed to provide confidentiality. We're not hiding the text. For example, if I apply the AES CBC MAC to this message, this is what I will obtain. It's a string of 128 bits, same size of an IPv6 address. So this is what a tag is for this message here. When we use a tag, we send the message and the tag. Of course, the tag doesn't mean anything, but the message is sent in the clear text, in the clear. So an attacker is still able to see the message. As I mentioned, it may be a good idea to add encryption to authentication, not just to authenticate, because you want to give the least possible amount of information to your attacker. If you use a tag, a strong cryptographic tag like the one I've shown, it will be quasi-impossible for an attacker to forge messages, to send you wrong messages. But the attacker will see all the things that are happening in your smart grid, for example. So if you want to do encryption, which we have seen before, the idea is to do both. Now the question we will address is, how can we do both? Here is the simplest way to do both. I have a message to send, reading from PMUs, for example. I can encrypt them with one key. I will obtain a ciphertext. And I can also create a MAC with another or similar technology that will use also its own key, capital L, and then I will send a tag. The tag will be sent in the clear. The ciphertext is sent in the clear, but since it's encrypted, it's just appearing as a random sequence of bits that is not very informative for the attacker. This is what we do if we do encrypt and MAC in parallel, done in some technologies like SSH. If we do this, we observe that the tag is sent in the clear and is completely independent of the ciphertext. Another way to combine is to say, well, I could first compute the tag using the key capital L. Then I could merge the message and the MAC. When I say merge here, it just means add the MAC at the end of the message, so it concatenates, and then encrypt the resulting message that is now large. Now, the receiver will first need to decrypt. The decrypted message will contain the tag that will then be verified. Here, in contrast, you decrypt the message independently of the verification that you do. This is called MAC, then encrypt. It's used in some security software. Another method here is encrypt, then MAC. So I first encrypt the message, I obtain a ciphertext, and I apply a verification to the encrypted message instead of to the clear text. And then I can send the tag in the clear, but this is the tag of an encrypted message and the message in the clear. The question is, which one should we use? Does it make a difference to use one or the other? Should we use one or the other? Well, to know, apparently the three look okay, except of course attackers have infinite imagination and have found ways to attack things that make some of those combinations less good. One of the attacks consists in trying to break the encryption scheme by injecting fake ciphertext. So assume you don't know the key, but you have the software, because AES, for example, is software that everybody can have. So if I give you a message, you can try to decipher it. You could also, in some cases, have the possibility to look at the result of what is done by the system you're trying to attack. You can send random messages to the system you're trying to attack. Of course, if the random messages have not been encrypted with the correct key, the message that you're trying to attack will discover that the messages that are sent look just like garble. They don't look like PMU measurements, but they look like garble. In particular, if you send messages that are malformed because the padding is incorrect, what is padding? Well, we've seen that AES is a block cipher, so it has to create blocks of 128 bits. What if your message is not a multiple of 128 bit? 128 bit is 16 bytes. So if your message is just 10 bytes, for example, or 2001 bytes, then you will need to make it a multiple of 128 bits by adding a number of dummy bytes. So that, because you cannot have a fraction of a block to it. This is called padding. Those are blocks of bits that were not present in the original message. Typically, all protocols have a field to indicate what is the length of the message, or a field at the end of a message, like an image or something, to say, now this is the end of the message, so that we can pad messages. We can add extra things. It will not hurt the message that we're sending. But if you send a message that is incorrectly padded, For example, if the length does not correspond to what you see, there will be an error code that will be triggered by the receiving software. Attackers can use these error codes to gain some information on where what field is. Giving that in more detail would be too long, but this was done by one of our colleagues here at PFS, Serge Bonnet, who did a paper on the padding oracle attack against precisely the symmetric cryptographic scheme we have seen, that is able to get some information about the plain text by repeatedly generating a number of error messages. So it requires the adversary to be able to send a huge number of cipher texts and that the destination accepts them. Of course, many systems will protect themselves by not accepting huge number of errors, but if you have a system that does not, for example, if you are able to make a clone of the system and run it, such that you can run it as many times as you want while disabling stopping due to error messages, then you will be able to obtain some of this information. So this is called the padding oracle attack. In general, it's an example of what is called a chosen ciphertext attack. If you're able to choose exactly which text you send to the attacked system, you are making your system a bit weaker. So in this perspective, we can now reason which of those three things are better here. We see here that if I send the tag, if I create the tag independently of the ciphertext, then I could get some information here by sending as many ciphertexts as I want. Of course, the tags will be wrong, but if I can execute this decrypting software as many times as I want, then I will be able to do this attack here. The same will occur here, because here, in order to verify that the text is correct, I need first to decrypt it. So if I decrypt it first, I will generate those error messages that come when I'm decrypting something that is malformed. Here, one protection is to do this combination, because I send the tag of the encrypted message, so I can first verify the tag of the encrypted message. And if the encrypted message appears to have an invalid tag, then I simply will decide that it is, I will not decipher it. Because by trying to decrypt it, I might give some information to the attacker. So because of this subtle combination, we see that this is the best combination, the one that should be used. Why do I talk about this? I mean, this is to show that when we do things, when we combine things in cryptography, it's important not just to have a good key and implement cryptography here, but also to do it the right way, which, since we are not in the smart grid experts in cryptography, means rely on experts and therefore update your software whenever needed. This is the kind of complexity that we're exposed to. I think we've seen all of that. I don't need to repeat it. So let's try the speakup.info. Here is a little quiz. You should see on your screen, as soon as I've typed in the beginning of the title, you should see this. So SpeakUp is completely anonymous. That's the value. If I ask you to raise your hands, then some of you might not dare to say something that's obviously wrong, but there's still information in giving wrong answers. That's exactly what the attack does that I mentioned a minute ago. The attackers send wrong messages in order to see what's the reaction. So here, don't hesitate to send wrong answers. There will be a lot of information for you and for me. close in 5 seconds. So you should see on your screen the histogram of the answers. There's a tie between B and C. The correct answer is B, D of course. Sorry, between B and D. So the majority answer is B. A secure map guarantees integrity, and it's secure as long as we believe it's secure. Integrity means that it is impossible practically to forge collisions, to create a tag that would correspond to a message that you are the author of, instead of the one that was the legitimate message. It means it's secure against passive adversary. A passive adversary is one that is just listening to and observing everything. The active is the one who would try to forge the message, to transform the message, and would need to transform the tag. And the major advantage or the main function of a MAC is to make this impossible. If you change the message, you have to change the tag, but the tag will be verified with a secret key at the other end. And if you don't have the secret key, you are unable to compute a value that will be the one that will be computed by the verifier. That is MAC. Another question to wake you up on this Monday morning. You can give the answer as many times as you want. So if you picked I don't know, you still can choose something else. I'll close the poll in 5 seconds. And the unanimity says B, which is correct. This is what we said. Now that's a question about encryption, not about tag. And we know that CTR and CBC are two modes that appear to be equivalent to provide a nonce. And because of that, they rule out chosen plain text attacks. Chosen plain text attacks means attacks where we exploit the fact that a certain block would always be encrypted in the same way. So what we saw so far is, I would say, the easy part of cryptography, or the one that has been around for a very long time. It's not so easy to make something secure because the attackers are as smart as the providers of schemes. But essentially, the idea of symmetric cryptography is you mix a message with something that is secret and will make it appear random. And then if you do the mixing right, which we believe is the case with AES today, and if the key is long enough, because you can always do a brute force attack by trying all possible keys, as we saw with Julius Caesar, that had too short a key, if those conditions are true, then we believe it's secure. Of course, there can be ways in the mechanisms that leak some information, like we've seen similar things with Homer schemes, that if you gave, for tags, if you gave twice, if you have two examples of tags and messages, there is a mathematical relation between those. So of course, schemes like AES are trying to avoid those kinds of ways to attack them. But there remains a problem of the keys, essentially. If we use cryptographic, symmetric cryptography, we need to put keys everywhere. So keys are like passwords, but worse. Right? You need a key for every PMU, and the key in the PDC. The PDC needs one key per PMU. So who gives those keys and where do they come from? Any key that is used too long is going to become a problem, even if the key is very long. But if you use a key to encrypt a huge number of messages, and if an attacker can see the messages and the ciphertext, then you will gain more and more information about the key. So the keys need to be renewed once in a while, not too often, of course, not every second, but let's say every year. So the problem is, how do we concretely distribute all those keys? Plus, they need to be secret. There's only one way to have a good secret. It is to not share it. Right? But here we need to share it. We need to share between the two ends. And also we need to install it. So there is risk that those secrets are lost or corrupted. So the key distribution mechanism is one of the key problems that's motivated a smarter use of cryptography, which is called asymmetric cryptography. So asymmetric cryptography can be used for encryption or authentication. We have seen, just like symmetric key cryptography does, we've seen this today and last week. Now we will see the equivalent when we use asymmetric cryptography. Let's start with encryption. It looks very much like what we saw for symmetric cryptography, except now there are two keys. One that is used for encryption and one that is used for decryption. And the key used for encryption is public. You don't need to make it secret. That seems strange, but that's the magic of it. So if you use asymmetric cryptography to encrypt something, you use the public key of the receiver, and the receiver has a private key. This private key needs to be secret here. As for symmetric key encryption, we believe that for this to work, we must have the fact that recovering the ciphertext here without knowing the private key must be very difficult. Of course, knowing the public key should be impossible because the public key is public. Right? So if you use the public key to decrypt, that should not give you any information. There are multiple systems, essentially two families of them, RSA and DSA. RSA is based on prime numbers. DSA is based on elliptic curve cryptography, but both are variants of the same mathematical theory, which are finite field theory. Here is how RSA works. It uses a large, not so large, a prime number that must be a power of 2 plus 1. So it is this one. And computations will be done modulo this thing. It's a bit like Homer's cipher, except this one works, not like Homer's. So we do modulo computations. The public key is, so let's start with the private key. The private key is obtained by two prime numbers. So you pick randomly two prime numbers. Of course, they must be very large. If you pick 3 and 5, the attacker will try them first. So you pick very large prime numbers. Today, we think that for RSA to be secure, the key should be 2,000 bits. So each of the prime numbers should be of the order of 1,000 bits in length, which is very, very, very long. So you need a mechanism to find prime numbers. There are some. You know the prime numbers are a topic of interest for mathematicians, and there is no recipe for producing prime numbers. They appear to be completely random in the sequence of integer numbers. So that's your secret key. You choose two prime numbers, and then you multiply them, and you make that public. Right. That seems stupid, right? For example, if I say my public key is 33, you will probably know what is my private key. You will know that my private key is 11 times 3. Right? But if I say this is my public key, so this is a product of two prime numbers, in order to find them, you will need to factor this into prime numbers, which today is a very hard number, is a very hard problem. Factoring large numbers into their prime dividers is a known hard problem, as long as we don't have quantum computers. When we will have quantum computers, this will be easy. So RSA will not be valid. But today we don't have quantum computers that have more than a few bits. So that's the trick, right? So for example, if I give you 2.5 is 10, 11.3 is 33. If I give you 91 as a public key, can you find my private key?
Nice, 7 and 13.
7 and 13. So 7 and 13 are the two prime divisors of 91. There's only one factorization, of course, modulo the order, of a number that is the product of two prime numbers into its prime dividers. Of course, there are numbers that are not product of two prime numbers, like 16, for example. 16 is not equal to the product of two prime numbers. But recognizing that such a number is a product of two prime numbers is very hard, and it's even harder to find out or it's equally hard to find the two prime numbers that are this here. So this is what RSA is based upon. So the public key is the product of those two things. Now, it's based on the following mathematical computation. The plain text have to be mapped to a sequence of integers modulo the public key. So this public key is very large, so this is with a lot of space. Still, it's a block cipher, the block being of length, the number k here. So we translate the plain text to a sequence of integers using ASCII code, for example. And then the encryption consists in computing the plain text to the power e, where e is this, and take the residue modulo k. Those are very fast operations. Exponentiation is very fast, particularly if this is a power of 2, e plus 1, because computing the square of a number is a simple operation. It's m times m. Then if you do it again, you obtain m to the power 4. If you do it again, taking m to the power 4 as input, you will obtain m to the power 8, etc. You will obtain by a small number of steps, in 16 steps, in fact, you will obtain m to the power 16. And then you will multiply once by m, you will obtain m to the power this here. So by 17 multiplications, you obtain this here. So that's simple to compute. Computing the residue modulo k, that's doing the division, when we do the integer division that we learn in primary school. 22 divided by 7 is equal to 3, and the remainder is 1. I have 22 apples to divide into 7 people. I cannot divide exactly. There is one that will remain and that I will keep for me. So that is the remainder. There is an algorithm, which is the algorithm of division. That is easy to obtain. So that's easy to compute. That's very fast. The decryption is very difficult if you don't know the secret key, because we believe that computing the discrete logarithm is something very difficult. Discrete logarithm is the inverse. If I give you m to the power e modulo k, k is known, m to the power e is known, but finding m is very difficult. I have to try all the possible values of m, which are, there are as many possible values as this number. Right, so you have to try all of them, compute them to the power e. Each operation is simple, but you have an astronomically large number of such operations to do. So we believe this is hard to do. It's easy to do if you know the secret key, thanks to what is called the Chinese remainder theorem. The Chinese remainder theorem tells us that if I give you the encrypted text, C, and if I compute its f power modulo k, so the power f, where f is a magic number, which is the inverse of e modulo this thing here. So that seems a bit magical, and we don't have time to go through it, but you can see that its complexity is simple. So once I have the secret key, I compute the product or the least common multiple of p minus 1 and q minus 1. P and q are the two integer, the primes factors of k. That gives me little k. Then I take e, which is well known, this number, and I take the inverse of this. What is the inverse? Well, the inverse is something that it's the inverse of e. That means something such that e multiplied by f is equal to 1 modulo k. Right? For example, 3 multiplies by 7 is equal to 21. Modulo 20, 21 is equal to 20. So 3 is the inverse of 7 modulo 21. So this is a bit atypical operations, but we know how to compute inverses using an algorithm that has been known for a very long time here. It has to do with computing greatest common divisor. So before people had computers, they had compute those things, and they had found algorithms for doing it. So once you have this magic number f, you take the ciphertext to the power f, and bingo, it's exactly equal to k. Because c to the f is m to the ef, and e multiplied by f is equal to 1 plus a multiple of k, and therefore this will be equal to m modulo k. Let's see what Lisa would do if the private key would be 3 and 11, which of course is not large enough to be safe, but is small enough so that we can understand the example. The public key would be 33, and imagine for a second that the attackers are so stupid they cannot know that 33 is 3 times 11. The encryption requires to compute little k, which is the least common multiple of p minus 1 and q minus 1. So 3 minus 1 is 2, 2 and 10. So the least common multiple of 2 and 10 is 10. We could just use the product, 2 times 10, that's 20, but that would work also, but would give computations that are a bit longer. So we take the smallest multiple. And then we need to find what is the inverse of e. Here the exponent was 7. 7 is the one I chose here for simplicity. The inverse of 7 modulo 10 is 3, because 3 times 7 is 21, which is 1 modulo 10. Modulo 10, we obtain just the last digit. If I divide 21 by 10, the remainder is 1. So the encryption consists in putting the message to the power 7, which is the constant of the scheme, modulo the public key, and the decryption consists in taking the ciphertext to the power, the secret thing that we have built from the P and Q, to the power 3. So for example, if I have this text, bonjour, I translate it in whatever code. Here I took a simple code where A is 1, B is 2, etc. That gives this sequence of numbers. I take all of those, of course the numbers must be less than 33 minus 1, if I take modulo 33. I take this to the power 7, so 2 to the power 7 gives something, that modulo 33 gives 29, etc. We find all the remainders here, and that's the ciphertext. To decipher, I do this to the power 3, and modulo 33, that will give me exactly those numbers. If I go back from the numbers to the text, this is how we'll do it. This is how RSA works, except of course RSA doesn't use 33, but uses a key like this one. Here. We believe that, as I mentioned, it's safe enough in the sense that if the key is very large, it's impossible to break the thing, because we believe it's difficult to do the factorization into prime numbers. Surprisingly. Right? That's the magic of prime numbers. To achieve that goal here, because people have been working very hard on factoring integers into their prime numbers, so there are algorithms that work better than the brute force. Therefore, you need to have very large keys. 2000 bits is believed to be sufficient today with today's computers, non-quantum computers. There are alternatives that are based on similar but a bit more complicated mechanisms, but similar. They use similar ideas of group theory, but they're able to have much shorter keys, which is more convenient. This or that are equally susceptible to attacks with quantum computers. So when the quantum computers are a reality, we will have a problem in the internet and in smart grids and everywhere. We'll need to change, hopefully somebody will find an alternative and you'll change the software. Public key cryptography is, of course, feasible. It's encrypting and decrypting is not requiring huge computing power, otherwise it would not exist. But it is computationally more expensive than symmetric key encryption by 2 or 3 orders of magnitude. So if you do it routinely for every message you send every 20 milliseconds, people resist doing that. You don't want to have a very fast computer on your PMU just to do the encryption. So what people do is what is called hybrid encryption. This is also what is done when you go for e-banking, for example. Instead of using the asymmetric cryptography to encrypt every message, we will use asymmetric cryptography to create a secret key. So that will solve the problem I mentioned before. How do I distribute the key? When you go to your bank to do something, or when the PMU sends some data to the PDC, it uses secret keys, but those secret keys are created dynamically for a few minutes for the time of your session at the bank. And next time you connect, or if you stay idle for some time with your bank, the key will be destroyed and you'll have to start it again, creating another key. How is the key created? Well, first we start with private and public keys. So the public key of the bank is known by your browser. We'll see how a bit later. So you know this public key, since it's public. Of course, the bank hopefully keeps their secret key secret. Well, that's the job of banks, of keeping secret secret. So they're very good at that. Once you know the public key, you choose a session key at random. So using some cryptographic random number generator, you choose a completely random number. That will be the session key. So very hard to guess by anybody because it's completely random. But then the problem is I need to send it to the bank. And because the bank doesn't know it yet. We do that on the client side rather than on the server side. That's a typical design that we find in all client-server applications. You want to put the compute-intensive tasks on the client side and not on the server side. Why? Yes?
Because if there are a lot of users, the computation on the server side will be huge.
Exactly. If you have millions or hundreds of thousands of users, you also have hundreds of thousands of computers and CPUs on the other end. So it's better to use this 100 of thousands of CPUs to do the compute-intensive work rather than having it done on the bank. So all servers typically try to offload as much work as possible on the client side. So here, the work that is to be done is to pick the session key randomly and encrypt it and send it to the bank. Now the bank will still have some work which consists in decrypting it and storing it in temporary storage as long as the session is alive. And if this is encrypted with the public key of the bank, only the bank can decrypt it. So this is secure. Any attacker who sees Y will still not know what is the secret key if the attacker doesn't know the private key of the bank. So this L is secret. Now we have a mechanism to create a shared secret between two devices without revealing the secret to the outside world, which is one of the primary usages of asymmetric cryptography. Now that we have the secret key, I can encrypt the messages that I'm sending. I can use it also another key obtained in the same way for creating validation tags. And then I can send the message to the bank that will be able to decrypt it here. Because typically here, we will need to do that for one session, whereas here we will have possibly a large number of messages. So that's a very typical combination that is called hybrid cryptography. We use something expensive to create a secret, and then we use that secret a large number of times. Voilà, this is our first use of private key and public key cryptography, also called asymmetric cryptography. A few questions on that? Back to speak up. I close in 5 seconds. And obviously the question is C. Well, I say obviously, but as we will see, sometimes we use the private key, sometimes the public key, depending on what we will do. We'll discuss that after the break. Here, for encrypting, we use the public key of the recipient of the encryption, because we want to make the things not readable by anybody else than the recipient. So the recipient will have a private key, so we must use a public key, which must be the one that corresponds to the recipient. Last question before the break. I close the poll in 5 seconds. And the correct answer is F. If we have n devices that really need to talk to each other, and you want to use confidentiality, then each of the devices needs to have its own private key and publish the public key. So we will have n private keys if we use asymmetric cryptography here. In contrast, if we use symmetric cryptography, we need one key per pair of devices. So n times n minus 1 over 2, so order of n squared. So that's one of the major interests and goals of asymmetric cryptography. We will see another one after the break. So we do now a break and resume at 10:15.